Hello everybody, and welcome back to another Big Ideas lesson. Today we are starting Unit 10, which is all about circles. Now, we might all know what a circle is by identifying it, but does anybody really know how to define a circle? What makes a circle a circle? Well, a circle is defined very precisely. It is defined as the set of all points equidistant, meaning the same distance away from a center. It's the set of all points equidistant from a center. So let's say I have a center here, and I wanted to make a circle. By the definition of a circle, I could make a bunch of dots 2 inches away from this circle, all in random directions, and I would eventually end up with a circle. Of course, it would take a very long time to do, require a lot of extra work, so instead of dotting every single possible point around here, which you can barely really see, a compass is what keeps that distance the exact same the entire time and allows us to make a circle. So really, a compass is just a ruler that pivots on a side. In the example here, I want you to make the center of a circle, and let's call it point P. Like so. We will always label the point in the middle of our circle, and that's what actually gives the circle its name. In this case, it would be called Circle P. We are going to be doing some proofs this unit and writing some sentences, so anytime we're trying to shorten this, the symbol for a circle is not just a circle, because that could be a letter O or it could be the number 0. It's a circle with a dot in the middle. This is Circle P. Perfect. Now, we mentioned that all the different sides of a circle are the same distance apart. They're equidistant. This side and this paper looks like it's about 1.5 inches. If you were to connect up one side of this circle to the middle, you would end up with something called the radius. The radius is formed anytime you make a line segment with one part on the outside of the circle, one part touching the center. So by definition, a radius is a segment whose endpoints are the center and any point on the circle. A segment whose endpoints are the center and any point on the circle. We are going to call this our radius, and for most applications, our radius is going to be given the variable r. Now keep in mind, all different radiuses are the same length. The plural of radius is technically radii, and it's spelled like this. All radii on the same circle are congruent. So this radius would be the same as if I drew it over here. If I drew it over here, it'd be the same length. If I drew it on the other side, it'd be the same length. It's all going to be the same length. Cool. Most of us are familiar with those words, but very few are familiar with what a chord is. So allow me to show you. Imagine making a radius, but not making it go to the middle of the circle. Instead, imagine it as 2 endpoints that are both on the edges of the circle, like this. If I were to connect up any 2 endpoints on the edges of the circle and draw a line segment, that would give us a chord. This is a chord. So, by definition, a chord is going to be a segment whose endpoints lie on a circle. So both endpoints have got to be on the circle, and it's also got to be a line segment. So no lines, no rays, just a segment. That's a chord. A lot of us are also pretty familiar with what a diameter is. A diameter is what happens when you have a chord that also passes through the middle. It basically is a chord that goes across your entire shape, your entire circle. So I'm going to draw, let's actually make the diameter right around here. There we go. I'll draw it in purple, just because. This is a diameter. It goes through the center of the circle, and it is a chord. Let's call this diameter D. And that's usually how we're going to abbreviate the diameter in this unit, is the letter D in lowercase. There's our diameter. So, let's fill in that definition. According to the definition, a diameter is a chord that contains or passes through the center of a circle. It's a chord and it goes through the center. It's a diameter. We've got two more definitions that we are going to discuss before we try to label some on our own. It's a lot of definitions, I know. This next definition is a secant. Now, next year in Algebra 2, you will learn that a secant is actually a trigonometric ratio, just like sine, cosine, and tangent. But we don't talk about that here in this class. Instead, when we say secant, we are specifically referring to this. A secant is any full line that crosses through two endpoints on a circle. This is a secant because it touches our circle twice and is a full line. We also won't be doing too much with secants in this unit, but that is what it is by definition. It's basically if a chord was extended into a line. So, by definition, a secant is a line that intersects a circle twice. It's got to be a line. Last but most certainly not least, we do recognize this word, tangent. Tangent is another one of our trigonometric ratios. But when we talk about it here, even though it is heavily related to the ratio, we're not really going to use it much in that way. No, when we say tangent, we are thinking of this. I got to be very precise while I draw this. There we go, that's about right. There we go. A tangent is a lot like a secant, except it's a little bit more flexible. By that I mean, a tangent is a line or a ray, meaning a line with just one arrow, or even a segment that intersects a circle at one point. So imagine this green line as just barely touching, barely even grazing our circle. That is what a tangent is. Now that one point is also called the point of tangency. So it intersects a circle at one point, the point of tangency. So here's our green tangent. In this case, the tangent is a line, but you could also treat it as a line segment between 2 points, or a ray if you wanted to. And this here is our point of tangency. Very cool. We're going to actually work a lot with tangents today because they have some very fun properties with them. But before we do that, I want us to work on identifying all these parts in an actual circle. So let's take a look at exercise 1. I want you to pause the video and see for yourself if you can pick out which lines, segments, and rays match up with the descriptions here. Then, for these two, you're going to give what part of a circle each of these are. Is it a radius? Is it a tangent? Is it a diameter? Is it a point of tangency? Pause the video here and see how you do. Alright. So, with regards to circle C, if we're looking for a diameter, we are specifically looking for a chord, so a segment, that passes through the center of the circle. Luckily for us, we see there's a chord that ends at points A and B and goes right through the middle. So, line segment AB is a diameter. What's a radius here? Well, the radius is any point on the circle that connects to the center of the circle as a line segment. A connects to C, so AC is a radius. BC is also a radius, so it doesn't matter which one we pick, they're both the same length. Our radius is AC. Next, for line AG, you want to pick out what that is. Well, this one looks like it's a line, a full line, that crosses through 2 points on the circle. We call that a secant. Finally, if we're looking at ray DE, we don't care really that the arrow goes off towards D as well. We are talking just about point D going on forever through point E. And because it's only touching at one spot, we know this is a tangent. Cool. Now here's where things get a little bit interesting. We're going to make 2 theorems that involve a tangent. This is going to come super in handy for us because we're going to be using these tangents pretty frequently. For this, I'm going to just draw one circle to capitalize on both of these problems. So here we go. I'm going to make this circle here. Doesn't need to be perfect, but I'm doing these for recording, so I want it to be as perfect as possible. And that'll do fine. I'm going to find the center of the circle, or at least what I think is about the center of the circle. And it's looking like about there. Close enough, right? And let's call this point Q. Now, here's the deal about tangents. Let's say I drew just a random tangent on this side of the circle. Just a tangent line. I'm going to make it cross through this point here. I'll say point P is the point of tangency. And I'm just going to make it a line segment, just to not overcomplicate things. Cool. This is our tangent, which I'm going to call line L. Now, here's the fun part about this. If I was to now draw a radius to this tangent, what do we predict will happen? If I draw the radius, which will connect the center of my circle to this tangent, well, hang on a second. Well, first off, I drew it a little bit inaccurately, so I'm going to bolden that line a little bit. There we go. This looks like it makes right angles. And as a matter of fact, it is guaranteed to. Anytime you have a tangent, it is always going to be perpendicular to the radius. That's kind of cool. This is the tangent line to a circle theorem. And it goes like this. A line is tangent to a circle if and only if it is perpendicular to the radius at its endpoint. A line is tangent to a circle if and only if it is perpendicular to the radius at its endpoint. Perfect. What this means is, if you have a tangent line, you have a right angle guaranteed. It also means if you have a right angle, this is guaranteed to be a tangent of your circle. The last theorem that we are going to be discussing is a bit trickier to draw, so I've really got to be precise here. But I'm going to draw it like so. The external tangent congruence theorem works by having an external point, a point that's not actually inside of the circle. Let's call this point S. I'm going to make two more tangents, both of which will connect up to S. So we see here that if I draw this out, there we go. That is a tangent segment that connects to an external point S. And if I'm precise enough, let's see, it should be right around there. Close enough. There we go. I've just made two more tangents. I want to call them tangent M and tangent N. This looks like an H. There we go. What do you notice about these two tangents? I mean, ultimately, this is the only tangent that would fit through point S, right? If it was tilted a little bit more, it wouldn't touch point S. Or if it was tilted up here, it wouldn't touch point S. We may notice that these are about the same length. If I drew them exactly correctly, they would be exactly the same length. But for right now, I would say that's actually pretty dang close. Here's the rule. Anytime you have an external point and you draw two tangents from your circle to that point, those two tangents are going to be congruent no matter what. Tangent segments from a common external point are congruent. Very nice. Let's flip the page and take a look at some examples to see how we can use these theorems. So in exercise 2, it asks us to decide if line segment ST is tangent to circle P, and to explain our thinking. Well, let me draw the tangent in green. We're saying that this line segment, ST, should be tangent to circle P. How can we decide that? Well, according to the tangent line to a circle theorem, a line is tangent to a circle if and only if it's perpendicular to the radius. What's our radius? Well, since TP touches both the center and the edge of the circle, that's our radius. And we need to decide if this angle here, angle T, is perpendicular, or is 90 degrees. How can we do that? Well, if you recall last unit, we've actually done something very similar to this. We learned that if you can utilize the Pythagorean theorem on a triangle, then the angle must be right. It must be a right triangle. So to test out if this is tangent or not, we should build our Pythagorean theorem. A squared plus b squared equals c squared. If this was a right triangle, the longest length, 37, would be c squared. That means the other two are legs, so 12 squared plus 35 squared. And we're not sure if it equals 37 squared. So I'm going to put a question mark over it. All we need to do now is calculate this out. So here I've got my trusty calculator. Let's calculate 12 squared plus 35 squared. 1,369 is this side. Now we should calculate 37 squared and see if they're equal. If they're equal, it's a right angle. If the hypotenuse is bigger, it's an obtuse angle. And if our hypotenuse is smaller, it's an acute angle. But we don't need to worry here. This is exactly 1369. So yes, indeed, these two are equal, which means angle T is a right angle. These two are perpendicular. So, ST is tangent to circle P, since line segment ST is perpendicular to line segment TP. Nice. Let's move on to exercise 3. Now, I'm going to warn you, this is going to require actually some pretty heavy math. Not the heaviest we've seen, certainly not as heavy as Unit 9, but it's going to require us to call back to Algebra 1. So, I'm telling you right now, points B and P are points of tangency. That means that no matter what, AB is a tangent. So we're good on that. We have to find the radius of this circle. Well, if we know that this is tangent, and we know that this is a right triangle, it's sort of like the opposite of before. Before, we knew it was a right triangle, so we know it's tangent. Here, if we know it's tangent, we know this is a right triangle. So, can't we just set up the same thing that we've been doing? A squared plus b squared equals c squared? Well, the answer is yes, but that things are a bit complicated on this one. For starters, let's identify what our legs are. So our first leg is our radius, r. So I'm going to call it r squared. The second leg, it appears, is this one, the one next to the right angle. AB, our tangent. So I'm going to call this b squared, or 80 squared. Then what is our hypotenuse? Well, be careful. This measurement of 50 feet only covers this much of the hypotenuse. The entire hypotenuse is this 50 feet length and a radius. In other words, to represent this hypotenuse, c squared, we would write it as r plus 50 squared. There we go. Okay, Mr. Strager, so what? This is pretty easy to solve. Well, maybe, but I want to remind you all of something that's often forgotten. Let's see what we can do. I'm most concerned about this r plus 50 side. If we have r plus 50 squared, the question is, how do we simplify that? And I will let you know, there is a right way and there is a wrong way. The wrong way is actually what most people might think of first. R squared plus 50 squared. Not correct. Squares don't work the same way as just coefficients. You can't just distribute them to everything. No. And let me show you in a way that proves it. Let's say instead of r and 50, I had 3 and 5 squared. Now we all know that 3 plus 5 equals 8, so this really is 8 squared, or 64. That's the correct answer no matter what, because we can just simplify it. If we were to try and distribute the square here, we would end up with 3 squared plus 5 squared, which is 9 plus 25, which is not even close to 64. It's 34. This is why you may not distribute an exponent. So what can we do instead? Well, this is going to require us to have some knowledge about what r plus 50 squared really means. R plus 50 squared is just 2 copies of r plus 50 being multiplied together. R plus 50 times r plus 50 is r plus 50 squared. This is where, in Algebra 1, we learned to double distribute, also known as FOIL. This is where we learned that we want to make sure we distribute the r to everything in our second parentheses, and then once we're done with that, we'll distribute the 50 to everything in parentheses. So let's do the r first. To distribute, we are multiplying, so what's r times r? R squared. What's r times 50? Well, that's just 50r. We have now distributed the r to everything in the second set of parentheses. I like to cross it out so I don't forget that I've already dealt with that. Now, the only thing left to distribute is this 50. So we will distribute the 50 to everything in the second set of parentheses. 50 times r is just 50r, and 50 times 50 is 2,500. Last, we check to see if anything simplifies, and, well, it absolutely does in this one. We end up getting r squared plus 100r plus 2,500. Nice. So that's how we deal with r plus 50 squared. R plus 50 squared means you have to distribute r times r times 50, 50 times r, 50 times 50. Sorry for that little bit of a long refresher, but let's get back to the problem. So what does this mean? Well, it means we get a long equation. R squared sticks around. 80 squared is just 6,400. And we discussed that r plus 50 squared is actually r squared plus 100r plus 2,500. Oh Lord, how do we solve this? Well, you may recall as well from Algebra 1, the only way to solve for r in this case is to move all the variables onto one side. So, we have 3 different iterations of r squared here, and r here. I'm going to move the r squared off of my left side by subtracting it. That'll cancel it out, right? But wait a second, what happens when I do minus r squared to the other side? What's r squared minus r squared? These also cancel out. So actually, we don't need to worry about the squareds. All we have is 6,400 equals 100r plus 2,500. From here, we can just subtract 2,500 from both sides, giving us 3,900 equals 100r. And finally, to get r by itself, we can just divide both sides by 100. r equals 39. That's our radius. Perfect! That's how we tackle this type of problem. It requires a little bit of past knowledge with this r plus 50 squared, but we can make it through. So I'd like you to pause the video and try out B. Come back in a moment to check your answer. Did we get a radius of 15? If so, you absolutely nailed it. Nice. Exercise 4 involves the other theorem we learned today, the external tangent congruence theorem. That's the one that says if you've got different tangents that all meet at a common external point, those tangents are congruent. So these problems are actually easier than they look. If we are told that points B and D are points of tangency, that means these are two tangents that both meet at point A. They have a common point. That means they are congruent. And anything that is congruent has equal measures. So we can say 2x plus 7 equals 5x minus 8 because they are congruent to each other. And that means we can now solve. We can subtract 2x from both sides, giving us just 7 equals 3x minus 8. We can then continue by adding 8 to both sides. When we do that, we get 15 equals 3x. And last but not least, we can divide both sides by 3 to get x equals 5. You could also check your work by plugging it back in and seeing if the two sides are the same. 2x plus 7 is 2 times 5 plus 7. That's 17. 5x minus 8, that's 5 times 5 minus 8. That's also 17, so we know we did it right. Part B is a little bit trickier. I want you to pause the video and see what values of x work for part B. Let's take a look at it. In part B, we know that since these are both tangents, and they're meeting at the same point, that their measures equal each other. So we start solving. I subtract 4 from both sides to get 2x equals 18. I then divide by 2 on both sides to get x squared equals 9. Now, to get x by itself, I have to take the square root. But remember the rule about square roots. Anytime you are creating a square root symbol, you are making a positive and negative answer. X equals plus or minus 3. So there we go. Whether x is positive 3 or negative 3, we can plug it back in, and these two sides will be perfectly tangent to each other. Nice. Let's take a look at the final example for today. So, this is sort of a definition. I wanted to put it in the definition section, but I'm going to be honest, we won't really use these that much more outside of this section, so let's take a look at it together. This will be in the homework, but we will not be seeing it too much outside of that. A line or a segment that is tangent to two circles is called a common tangent. So, what does that mean? This means that if you have a tangent that runs across two circles, it's a common tangent. Now, the definitions here for common internal and common external tangents are a bit complicated. But let me allow myself to diagram it, and then you can decide for yourself. If I'm looking for a tangent line that goes across two circles, what I'm really looking for is some line that will touch each circle only once. So if I can make a tangent over here, it'll touch the left circle only once, but it doesn't touch the right circle at all. Watch what happens as I keep moving my ruler and traveling around. I will eventually find a point where my ruler touches both circles without passing through the circles. This is what we can use to make a tangent line. This is a common tangent because it is tangent to both circles. We call this type of tangent an external, or common external tangent, because it's on the outside of both of the circles. It is on the exterior of both, and it kind of looks like a face. Is there another common external tangent in this diagram? There sure is. If we take a look at the top of the circles, is there a line that could connect the tops of these circles? The answer is yes. If I make sure that I'm not passing through the circles, just lightly tapping both of them, like here and here, I can make a second line that goes across the top without going through. Think of it like rolling some wheels onto different surfaces. The surface is the tangent, and these are our wheels. These are both common external tangents, and we have two of them. Two common external tangents. But believe it or not, there are some hidden ways we can draw a line that touches each circle once. Let's continue this idea. Here's my ruler, and if I keep tilting it, I'll eventually find a spot that'll just touch the circles once without passing through. Right now it is totally passing through the middle of the circle. But if I keep rotating it, notice how this chord here keeps shrinking, and shrinking, and shrinking, and shrinking, until, look at this. Let me draw a point on both of these circles so we can see what I'm talking about when I say look at this. These 2 points. You can barely see them because I didn't really mark them off very well. These 2 points are a spot where I can place my ruler in between them, and it only touches once. Look at this. We have made an internal tangent, a common internal tangent. A common internal tangent is a tangent that crosses in between the 2 circles. So if it's in between, it's internal. Is there another common internal tangent? If you're ever in doubt, just keep rotating your ruler. I'm rotating mine around the left circle very slowly until I see a spot, aha, where it looks like I could draw just a dot that touches the ruler and another dot that touches the ruler on the other circle, and I could make another common internal tangent. Bam! There's another one. So here we have 2 common internal tangents, which means, in total, if you have 2 circles that are separated by each other, or from each other, you have 4 common tangents. What I'd like you to do is I'd like you to work on these next sets of circles where there's something slightly different. Double check to see if there are any common tangents that you can draw, and try drawing them. Pause the video now and see how you do. Alright folks, allow me to show you all of the common tangents on these diagrams. In part B, there are actually 2 common external tangents, which can be drawn here on the left side of these circles, and here on the right side of these circles. Both of these are external because they're not in between the 2 circles. Now the question is it possible to find a spot in between them where there's a tangent? Well, assuming these circles are only touching at one point, these 2 circles could be basically tangent to each other, right? In fact, there is a vocabulary word that says tangent circles are any 2 circles that are just touching at one spot. Whenever you have 2 circles that are tangent to each other, since they're both just touching at one spot, you can make a line that crosses through that one spot, only touching each triangle once. here in B, there are 3 common tangents. Cool. Now, granted, anytime you have 2 circles that intersect each other this way, where you have 2 points of intersection, there's no in-between the circles anymore. This is basically a Venn diagram. There's no in-between that we can make a tangent between. So we are only going to ever have the 2 external tangents along the outside. The one that goes right here, there we go, a little crooked, and the one that goes right here. These are the 2 common external tangents. There's no internal tangents you can make that would only touch each circle once without crossing through. So we would say here, there are 2 common tangents. And with that, that's the end of lesson 10.1. I hope you guys enjoyed the lesson. Have a fantastic rest of your night, and I'll catch you in the next one.